So, hello everyone, welcome to all, and let us all welcome our speaker Agniva to deliver third lecture in the series Introduction to SCV. Agniva will be talking about holomorphic extensions in SCV. Over to you, Agniva.
Yeah, thank you. Let me just share the screen. Just a sec. So, is it visible, right?
Yeah,
And I'm audible.
yes,
Yeah, good. So, okay, thank you everyone for joining. So last time we forgot to record. So I'll do a brief recap of the what we did last time. So, last time we uh, talked about power series, and we didn't complete our full discussion. What we talked about, we basically talked about the power series and their domain of convergence. Domain of convergence means where a power series, what is the largest sort of domain where a power series actually converge. That's it. So now, what today I'm going to talk about is that the rest of the discussion about domain of convergence. But what we last time also talked about is a necessary condition for a uh, domain to be a domain of convergence of a power series, and we saw that that condition is what known as the complete Reinhardt domain. Uh, and we also saw that if you have a Reinhardt domain and you have a holomorphic function in the Reinhardt domain, then that function has a Lorentz series expansion. It's a global Lorentz series expansion. And from that, you also deduce that if the Reinhardt domain has the extra property that it intersects all the elementary planes, that is Zn equal to 0, then that admits a power series expansion, which is a very critical result actually. That is, it has a global power series expansion. And we have also said that we actually saw that the only complete Reinhardt domain in complex plane are the disk centered at 0. Uh, we also like briefly talked about at the end is that from 4 we can actually talked about that we cannot have a finitely many singularity of a holomorphic function. So holomorphic function, if it is not holomorphic at a single point or finitely many point, that holomorphic function extends to those points. So there is no finitely many singularity of holomorphic function, which is very unlike from the complex analysis. The complex analysis, the theory of singularity or the isolated singularity is so rigid, right? But here you cannot have isolated singularity. That's what I meant. Now let's talk about today. So today what we are going to do, we are going to complete our discussion on the domain of convergence of a power series. So I start with a question, which is that are all complete Reinhardt domain a domain of convergence for some power series or not? That's a question, and the answer to this question is no. Otherwise, we had stopped our discussion last time itself. So there is one more necessary condition that we can impose on a domain of convergence of a power series. So just recall CS is, so suppose S is a power series, A alpha Z to the alpha, and CS is the domain of convergence of S. Then what I'm going to do, I'm going to give, so of course we have last time we saw that this is a complete Reinhardt domain. This is always going to be a complete Reinhardt domain. But what I'm going to talk about today is that there is another condition that you can actually impose, another necessary condition that you can impose on CS. And here comes a convexity kind of a condition. This is known as logarithmically convex domain. So logarithmically convexity. So what is this? So suppose the definition. So by name, you can actually understand what is this. So you have a domain. So basically what logarithmically convex means is that you apply, you have a domain, you have the domain has all the points and you apply log to all the points. You get a new domain and then check whether that domain is convex or not. That's it. So what this is, so if omega subset of Cn is a Reinhardt domain, then first define the log of omega. So the log of omega is defined as just all the points in Rn, because log will take a point to Rn such that zeta is log of mod z1, log of mod zn for some z1, z2 up to zn in omega. See that since it's a Reinhardt domain, z1, z2, zn in omega basically means that z1, z2, zn basically means that mod z1, mod z2 up to mod zn is also in omega. So what I'm basically doing, I'm basically considering suppose you have a omega as a domain and you are taking this map tau to Rn. What you are doing, you are taking all the z1, z2, zn and you are just mapping them to log mod z1 up to log mod zn. And you are just looking tau of omega. So that is going to be a domain in Rn. So it's a domain in Rn because log is open map domain in Rn. This is going to be a domain in Rn. And what is logarithmically convex means? Logarithmically convex means that this domain is log omega, this domain is convex. So a logarithmically convex domain, so definition, log convex domain, rather log convex Reinhardt domain. So it's defined as so omega subset of Cn Reinhardt domain is said to be convex to be log convex if log of omega is convex in Rn. Just change the orientation of it. So that's it. So the important point why we introduce this, the reason why we introduce this is that you can see that CS is going to be a log convex domain. So here is the theorem. This theorem is not very difficult. I'll show a sketch of the proof. So theorem is that we'll give examples. Don't worry. So theorem. So suppose omega subset of Cn is or basically I just write like this, that CS is log concave, convex. I'm saying log concave or something, log convex Reinhardt domain. So what is sort of the basic idea of this? The idea is pretty simple actually. So suppose you have 2 points. So what I have to show? So to show that log of CS is convex. If I take 2 points from log of Cx, how does it look at? So 2 points from log of Cs will look like, so there was 2 points from log of Cs will looks like log of mod zeta of 1 and say log of mod zeta 1 and log of mod zeta 2. So these are 2 points from log of Cs. So that basically means that zeta 1, zeta 2 is in Cs. That basically means what? That means that A alpha mod zeta 1 to the alpha, this thing is finite, and A alpha mod zeta 2 to the alpha is less than 20. So what happens over here? I think last time we also talked about it. If the series convergence, the series terms will be all bounded, right? They are absolutely bounded. So mod of A alpha I can always found a large m greater than 0 such that this is less than m, and mod of a alpha mod zeta 2 to the alpha, this is also less than m. Now what you do, you have to look at log of mod zeta 1 and log of mod zeta 1 and log of mod zeta 2. And what you have to show? You have to show that if I take any t between 0 and 1, I have to show that t log mod zeta 1 plus 1 minus t log mod zeta 2, both of, I mean, this particular element is in CS, log of CS. But that you can solve immediately from now. So what do? You basically apply mod of a alpha to the power t times mod of, so this is mod alpha, mod of mod alpha to the power t is less than m to the power t. And similarly, you apply 1 minus t, zeta t, 1 minus t, mod alpha less than 1. Now, I think you guess what you have to do. Basically, take a product and you are done. If you take the product and take the log, you will get that this thing, so if you take a product, it will be mod of a alpha times mod of zeta 1 to the t to the mod alpha times zeta 2 1 minus t to the mod alpha, which is less than m. But that's what you basically need, because now you apply a log and you get that log of mod zeta 1 plus 1 minus t log of mod zeta 2 is in CS. So now you can complete this. Complete. Just one line. So there is a little bit technicality, but it's fine. I mean, you can reduce it from here. So that's the important point. So the important point is that if you have a power series, the domain of convergence of that power series has to be log convex. Now let's look at some examples. So the examples are okay. Maybe before going to the examples, I want to just clear the elephant out of the room. Is that this is the most important theorem? Is that if omega is a complete Reinhardt domain, so up to all this, we have only talked about necessary condition, but here comes the sufficient condition as well. So suppose you have a complete Reinhardt domain, which is log convex, then omega is a domain of convergence of some power series S. Power series. That's it. So basically, what does it mean? That a domain of convergence of a power series has to be a complete Reinhardt log convex domain, and vice versa. And the opposite also is that if you have a complete Reinhardt domain, which is log convex, then that has to be a domain of convergence of a power series. So this is the sufficient condition. So this is the main point over here is that log convex complete Reinhardt domain if and only if it's a domain of convergence of power series. So that gives you a complete answer. What is the domain of convergence of a power series in higher dimension? It's just log convex complete Reinhardt domain. That's it. Now we'll go to example. Okay, this proof of this theorem. Okay, this is a little hard. Of course, you can expect that the sufficient condition in this case is going to be hard because we are asking something much more. We are saying that if you just have a complete Reinhardt log convex domain, I need to find a power series whose like the largest where that power series converges is omega. So that is a hard statement. So it requires what known as holomorphic convexity. So that is probably talked later on, I mean, later in some other lectures, requires what is known as holomorphic convexity. So, and this is beyond our scope right now. But you can understand the theorem. So the point is, let's look at some examples and some nice factor. So examples. The first example is that any convex Reinhardt domain is log convex. So I haven't put the word complete over here, but the important point is try to prove that a convex Reinhardt domain is always a complete Reinhardt domain. That's a good thing. So this implies complete, by the way. That's a good exercise. And so there's a little bit digression. So last time we always talked about mod Z1, mod Z2 axis. That we can always represent a domain which is Reinhardt in mod Z1, mod Z2 axis because they are rotationally invariant or invariant under the toric action. But this representation is sometimes a little bit deceptive because, for example, if I take a domain like this is just polydisk, a very bad straight line, but okay, this is a polydisk. Uh, this is of course a convex domain. It's just product of two convex domain. This is also a convex domain. It's just a ball inside part. But is this a convex domain? If I take this, if I draw a disk in mod Z1, mod Z2 axis like this, is this a convex domain? Any idea?
No, because you can take points. This is something like annulus. Means
Yeah,
it is
so
not convex.
this is not a convex domain. The point is, if of course, if you write down the equation, you will immediately see that it's not a convex domain. But I want you to think geometrically a little bit better. Is that so? When you draw something in mod Z1, mod Z2 axis, and when you have a Reinhardt domain, basically, at each point on the boundary, how do you think that in R? I mean, it's a C2 domain, right? It's 4 dimensional. I have drawn it in 2 dimensions. So what are the other 2 dimensions you can represent, or how do you the other 2 dimension you can actually represent? Is that you should think like at each point there are 2 circles that are associated to it. So at each point there are 2 circles that are associated to it. That's how you think about it. Now the important point is the circle has to be inside the domain, right? Because that's how the Reinhardt domain is defined. That e to the I theta 1, Z1 and e to the I theta 2, Z2 has to be inside the domain. But you can see that the circles are actually going out. So if I take a point like this, here if I take a point like this, if I take something like this, the circles are clearly going out of the domain. Now, the circles won't go out of the domain if you if if you draw a domain like this, because now the circles, if you draw 2 circles, they're always inside the domain, and that is exactly a complete Reinhardt. Your land on the complete Reinhardt setting. So why I said this, because okay, something is convex in mod Z1 mod Z2 axis doesn't mean that it is convex in the original domain. So sometimes this mod Z1 mod Z2 axis representation is a bit deceptive. But anyway, so this is one example. Next is you can immediately see that a convex domain, convex Reinhardt domain is log convex. It's not very difficult. If I give some concrete example, so if I take this domain, maybe just draw the domain. So it's mod Z1, mod Z2, and I draw like this. So what I have taken is that I have taken a union of 2 polydisks. So it's inside this part. So it's like, so maybe omega, if I really have to draw it. So it's like D012. So what does it mean is that it's basically, okay, maybe I just write in the expanded notation. It's a disk of 0, 1 cross disk of 0, 2 union disk of 0, 2 cross disk of 0, 1. So that's how I defined it. This is 1. This is 2, this is 1, this is 2. So there's a 2 union of this thing, 2 union of 2 polydisc, and this is not. So this is not log convex. Now, how do you see something is log convex? So what you do, you basically apply a logarithmic transform on it. So suppose you have a domain. So the way you go, suppose you have a domain, you have drawn the domain like this. You just go to the log scale. So if you apply the log scale, it is mod Z1 mod Z2. So you will go to, now you are in R2. So you apply the log scale, you will be in R2. So this is log mod Z1. This is log mod Z2. And this is minus log mod Z1 and similarly minus log mod Z2. So you go to the log scale and draw the domain. So if you apply the log scale, for example, you can check that if you apply the log scale over here, you will get something like, you apply log over here on this domain, you will get something like minus infinity cross 0 cross minus infinity log 2 union minus infinity log 2 cross minus infinity 0. So it looks like, okay, I'm pretty bad at this drawing. So let me just remove this. So it looks like something like this. Basically, it's two unbounded square. Basically, you get an unbounded square. So minus infinity. So log 2 is somewhere down here. Oops. Sorry. So log 2 is somewhere down here. So you basically get, to remove all this axis, basically get log 2 minus infinity cross 0. So it's like this. And log 2 is somewhere down here. So you some got something like this. So a domain you basically get is something like this. So you get a domain like this, and you can immediately see that this domain is not convex because this line is not there. So what you do, so if my question is that, okay, what is the smallest domain that contains, smallest logarithmically convex Reinhardt domain that contains this domain omega? What I am going to do over here is that I am going to I'm going to take a convex hull of this domain. That is basically, this is not convex, but I am taking the smallest convex domain that is contain this domain, right? So what is that? So that is basically, if I just join this line, if I just join this log 2 to log 2 line like this, then it becomes this domain become convex domain. Now what you do, but this is in log scale. I have gone to the log side. Now what you do, you basically go back to the domain by taking exponentials. Take exponentials and go back to the main domain. I mean, this domain. So this is your original domain, but you have extended a part. So you have, if you extend a line like this in the log, in a log scale, it will be, so how does this, basically this domain, how does the, how do you parameterize a line? It's like t times t comma 1 minus t, right? Now if you take the exponential of it, it's like e to the t comma e to the 1 minus t. So in this domain, you have to add a e to the t comma e to the 1 minus t. And how does a e to the t comma e to the 1 minus t looks like? If you just plot that in graph, you will get something like this. It's carved, huh? This is not a straight line. It's like this. something like this. So this domain is logarithmically convex, convex complete Reinhardt domain. Complete Reinhardt domain, or rather smallest logarithmically convex complete Reinhardt domain that contain omega. Or in other words, this is what a logarithmically convex hull is. So this is the logarithmically convex hull of domain omega. I hope this is clear. Why I am putting this effort to draw all this is because we know something. So we know, and that's sort of the main topic of today's and probably the next talk. So we know that if, for example, look at this domain only. So if I take F, which is holomorphic in omega, I know that F can be written as a power series. Why? Because it's a complete Reinhardt domain. A complete Reinhardt domain, there is a power series expansion of a holomorphic function. So for all z in omega. But look at the right hand side. Right hand side is a power series, right? Where does power series converge? Power series converge on a complete Reinhardt domain that's logarithmically convex, right? So power series cannot converge in here. This power series is not converging here. It converges something larger than this. And what I can say, at least it will converge up to this because that's the smallest logarithmically convex domain. So if I call this domain omega tilde, I can say that this power series converge at least on omega tilde. But what does that say? That is saying that the function which is holomorphic in omega, you can extend that function to a larger domain omega tilde. Now this is what holomorphic extension is. So you take any function f which is holomorphic in here, any function f which is holomorphic in this omega domain, you can at least extend that function holomorphically to omega tilde. So that's sort of the main point of today's talk, or rather, whatever the time left, I will talk about that, is that holomorphic extension of holomorphic function. Now you have seen this trend that whenever I start a new topic, I go back to one dimension, and I will again go back to one dimension, is that n equal to 1 case. And this is, I mean, at the first talk, I gave some differences and similarities of complex analysis and several complex variables. And this is probably one of the striking one and probably one of the influential one. So question 1, I'll start with the question itself. So question 1, suppose you have a domain in C, any domain. And if I take a P from the boundary of omega, does there exist a holomorphic function Fp on omega such that Fp does not extend across the point P? What does it mean? Does not extend holomorphically. What does it mean? If I take a domain like this, any domain you take, omega, suppose P is a point on the boundary. Suppose you are given, what I'm asking is that can you construct a holomorphic function depending on this point P, which does not extend across this point? So there, if I take a neighborhood around this point, the function does not extend holomorphically across that point. Now the answer to this question is very simple. The answer is yes. And the answer is that you basically take this function. So basically you create a pole at P. That's it. If you create a pole at P, you cannot extend this function across this point P holomorphically to a larger domain. You cannot do that, right? So that is something that you, easily constructed. But why can't you do this for higher dimension? As I last time also talked about, that in higher dimension you don't have isolated singularity. Here you have isolated singularity, but why can't you have exactly this kind of construction? For example, if I take the polydisk, if I take the polydisk, and if I just remove the point 0, 0, why can't I define fz to be fz1, z2 to be fz1, z2 to be simply 1 by z1? Why this is what is the problem with this? This suddenly at per point 0 blows up. Then what's the issue? Why can't you make exact construction like this, which I have just mimicked? Why you can't mimic the same construction for the higher dimension? What is the issue with this particular example? Any idea? So the problem with this is that this function is not holomorphic at a single point. It looks like it's only not holomorphic at a single point 0, 0, but it's not. It's not holomorphic on all the lines 0, z2. So on all the horizontal axis, this is not holomorphic. So this function is not holomorphic in here. This function is not holomorphic at the polydisk minus the point 0. So you cannot have this kind of a construction because you have an extra dimension which will always create a problem. Now I'll ask a harder question, and this particular question. Remember this question. This question is basically saying that if you have a domain, can you and if I give you a boundary point, can you always construct a function depending on that boundary point which does not extend across the point? The next question is a little harder, much harder in fact, is that, so if omega is a subset of C, does there exist f in holomorphic in omega which cannot be extend holomorphically across any boundary point? Now, what's the difference of this question 1 and question 2? Well, question 1, I was fixing a point P. I was asking for a FP. I was asking for one function which does not extend across any point. But for example, 1 by z minus p does not extend holomorphically across the point P, but it extends across all other points than P. It's a holomorphic function on the whole plane except the point P. So it extends everywhere except the point P. Now I'm asking something much more delicate. I'm asking that if I give you a domain, can you construct a holomorphic function which does not extend across any boundary point? So this dependency on the P is removed. So I'm basically asking a uniform function which works for all the points. Now this is hard. This construction is hard. And the answer to this question is again yes, because I am in C. Is yes. So in C, all the domains basically satisfy this condition and this condition. And this condition. Question 1 and question 2, the answer is yes. And in higher dimension, so when n is strictly greater than 1, you have already seen that answer 1 and answer 2 is false. Answer 1 and answer 2 is false. For example, if you take the polydisk minus the 0.00 minus the 0.00, then any holomorphic function over here extends to the whole polydisk. So there is something much more delicate happening over here. In terms of holomorphic extension, things are not so simple. Okay. So let me see what I want to talk more. Yeah. So let me define two things, and this is probably setting up a ground for the later talks. I mean, not. I mean, probably someone else will talk about it. Probably Ravi will talk about it. So two definitions, and they're like very, very important definitions. So two definitions. So this phenomena, when you cannot extend, has a name. When you find a particular holomorphic function which does not extend across the boundary, has a name. And these two definitions is the first definition, number 1. This is known as weak domain of holomorphy. Domain of holomorphy. So what is this? So sorry, that. So a domain, suppose omega is a subset of Cn, be a domain said to be a weak domain of holomorphy. Domain of holomorphy. So I'll write DOH for this domain of holomorphy. If for every boundary point, this is actually motivated by the question 1. So for every boundary point P, boundary omega, there exists a holomorphic function depending on the point P, such that for every connected neighborhood of P, or connected neighborhood U of P, there does not exist a holomorphic function H, which is holomorphic in U, such that H is equal to FP on some open set V, such that P is on the boundary of V. I'll draw a picture, it will be clear. I mean, it's basically the same. I mean, it just captures the same sense which I just talked about. Suppose you have this domain, you have this point P over here. What I'm asking that you need to find a FP which does not extend across this point. So basically that means that you have a domain U, you have a connected open neighborhood U of P, such that there does not exist a holomorphic function H on this U. So this is U. So this is U. What you are asking is that you don't have a function H which is holomorphic in U, such that which coincides on a open set here, which is V, with FP basically. So if it coincides, then basically by identity principle, you can say that it has already extended to a larger domain. So that's the main point over here. And so the important thing to remember is that for a weak domain of holomorphy, just make a box over here. For a weak domain of holomorphy, you are fixing a point P and you are asking for a particular function depending on that point P. So every domain in C is a weak domain of holomorphy. Now, strong domain of holomorphy, or sometimes it's just called the domain of holomorphy. Domain of holomorphy. So, a domain omega subset of Cn is said to be a domain of holomorphy if, okay, maybe just write it properly, to be a domain of holomorphy if, number one, it's a weak domain of holomorphy. It is a weak domain of holomorphy. Number two, it is more than weak domain of holomorphy. So it basically, what now I'm going to ask is that, can you find a one function which is not depending on P, which does the job? So what I'm asking is that, it has to be a weak domain of holomorphy, and the dependence of P on Fp is removed in the definition of weak domain of holomorphy. That's it. So what does it basically mean is that the domain of holomorphy basically means that if you have if your domain has to be said to be a domain of holomorphy, then it basically means you need to find one single function which does not extend holomorphically across any boundary point of the domain. Examples, again, I'm not going to prove this, and this is a very, very important topic in several complex variable. So examples of domain of holomorphy and weak domain of holomorphy. Number one is that, of course, any planar domain. Any planar domain. Polydisk or a ball or any convex domain, in fact. Any convex domain in Cn. This is important. So we have already discussed this. So if you have a logarithmically convex complete Reinhardt domain, you will always, what does that mean? If you have a logarithmically convex complete Reinhardt domain, that domain is a domain of convergence of a power series. So that power series, whatever that power series is, cannot be extended to a larger domain. But what in fact more is that it cannot be extended to any boundary point, across any boundary point. So any logarithmically convex complete Reinhardt domain is another example. Non-examples, well, you won't find any non-example in one dimension, because every domain in one dimension is a domain of holomorphy or a weak domain of holomorphy. Non-example in higher dimension, so this is all n greater than 1. Omega minus finitely many points. Finitely many points. Any complete Reinhardt domain that is not logarithmically convex. So if you have a complete Reinhardt domain that is not logarithmically convex, that is automatically becomes a non-example of a domain of holomorphy, because as I said, it has been already done, because what happens over here is that every complete Reinhardt domain, if you take any complete Reinhardt domain, every holomorphic function has a power series, and that power series will at least extend to the logarithmically convex hull, or the smallest logarithmic convex domain that contains that that domain. So it's no. This example, or rather, this is the main ground, or like this actually is the setup of the whole next talk. Is that if you take a domain omega, and this is a Hughes theorem, and you just remove a compact set. So if K is a compact set, and if this is connected, then it is not a domain of holomorphy. So what does it mean? So it means that you take any domain in Cn, and you remove a compact set like this. If you remove a compact set, making sure that omega minus k is connected, then every holomorphic function in omega minus k will actually extends to a function which is holomorphic in omega. So this, whatever you have made this, basically make a hole, right? It will extend, it will fill that hole. So I will write down the proper statement in a second. The importance of domain of holomorphy is that why this is so important. So why domain of holomorphy is so important? Domain of holomorphy is so important, or weak domain of holomorphy is so important. Is because it's not just only this extension property or non-extension property. It because it actually gives you a lot of geometric conditions, a lot of different geometric conditions, like geometric domains, in fact, or geometric conditions on domains. So in a later talk, later lecture, we will see that this particular phenomena, that when a domain is a domain of holomorphy or a weak domain of holomorphy, has a lot of connections to a lot of different avenues. For example, the first thing that came into mind is what known as a pseudo convexity or holomorphically convexity. So they are two different definitions, but they are all equivalent. So there are like 12 or 13 different equivalent conditions. Some of them are stemmed from analytic conditions. Some of them are from very, very geometric conditions. And very surprisingly, there is something called a D-bar problem, which we will talk about next day a little bit. And it turns out that it's a PD. It's basically basically you are asking solution to a PD. And it turns out that this PD is solvable with nice estimates whenever your domain is a domain of holomorphy. So it's something as a completely geometric. This definition, when I give this definition of domain of holomorphy or a weak domain of holomorphy, this is completely a geometric definition, but it has connection to completely different avenues of analysis, geometry, and many other things. So that's why this is sort of one of the highlighting topic in several complex variables. So just a little bit spoiler. So this is basically a spoiler to the next series of lectures. Sorry, I think Ravi will talk, and I'm sorry for giving this spoiler to everybody. That of course, a domain of holomorphy is a stronger definition. So domain of holomorphy implies weak domain of holomorphy. That's how you define domain of holomorphy. The spoiler is that the converse is also true. This is something huge, that if you have a weak domain of holomorphy, that implies a domain of holomorphy. So there is no point talking about separately weak domain of holomorphy and domain of holomorphy. They are the same notion. So this is amazing because the reason why this is amazing is that, so what weak domain of holomorphy says? Weak domain of holomorphy says that, okay, if you give me a point on the boundary, I will find you a function fp which is holomorphic in omega and does not extend across this point. Okay, very good. But From this function, if you do this for all points, if you just do this for all the points, how can you come up with a function f in holomorphic omega which does not extend across any point? The first thing probably came into your mind is to apply a partition of unity. You just patch them. You start to patch them, maybe take a countable tensor set or then start to patch them. But the problem with patching is that, and that's actually something that I talked in the very first day of the first lecture and like in first 5 minutes, is that there is no holomorphic cutoff functions. Because a function which is compactly supported and holomorphic, it's completely zero. So it cannot use partition of unity. So there is no partition of unity in holomorphic setting. So you cannot do this patching business and say that, okay, I have found a function for each point, depending on each point. Now I will patch them and I will construct a function which does not work for all the points. You cannot do that. So that's why this is a very, very delicate situation. And in fact, it's not very easy to prove this direction. I mean, you need a little bit much, you need to develop a more and more conditions, and then you can actually say that okay, weak domain of holomorphy is actually domain of holomorphy. So, okay, I want to last finish with one more thing. I think I have 10 more minutes, but again, I will not push to 6:05. So theorem, and this is next day. So this is something we'll talk about next day. Theorem is that suppose omega is a subset of Cn and n is strictly greater than or equal to 2. This will not work in one dimension as a domain, and a subset of omega is a compact set, compact subset of omega such that omega minus k is connected if f is a holomorphic function in omega minus k, there exists a function in omega such that ff is equal to f on omega minus k. So basically means that you take a domain and remove a compact set, making sure that omega minus k is connected. This is very important. This connectedness condition is very important. Then any holomorphic function on that sort of annulus kind of a domain is extend to the whole omega. That's an amazing result. For example, these things I haven't talked about, but there is another very important example of non-holomorphic, non-domain of holomorphy is that this is called Hartogs domain. Basically, union of it's a annulus crosser disk, union annulus crosser disk, and basically this domain, something like this. So this is again not a domain of holomorphy. Even you can use this particular theorem that this omega minus k, which is this, you have just removed this middle part, and what will happen if you take up function f in this green region, which is holomorphic in this green region, you can basically extend to this whole polydisk. So that's what known as the Hartogs figure, and this theorem is known as the Hartogs theorem, Hartogs extension theorem. Now then you may think like, okay, so next day will be just the proof of one theorem. So this is Hartog extension theorem. Next day will be just a proof of one theorem, but it's actually not. The reason why I chose this theorem to present next day is because the proof actually consists a particular tool, or rather a particular concept, which will be helpful in later lectures, which is known as a D-bar problem. And we will solve a version of D-bar problem on a very specific setting, which is basically the compactly supported setting, which is very, very, this is, if you really look at the original D-bar problem, it's nowhere near, it's very a baby version of it. But the importance is that it will actually introduce the D-bar problem. So I'll have the opportunity to introduce the D-bar problem and set up for someone else to present on that. So that is more or less today. I want to give a small exercise. You can now try this. exercise is that now you can try that zeros of a holomorphic function of a what happened to my pen? What happened to my pen? Okay, just a sec. Happens. Just a minute. Some glitches happening. What's going on? Okay, probably this is God is saying me to stop now. So yeah, probably it's something happened to my Apple Pencil. Okay, I'll stop over here. So the point is that I'll write down the exercise in the notes. So the exercise is that just prove that zeros of holomorphic functions are not isolated. So if you take any holomorphic function, the zeros are basically not isolated. We talked about this in last lectures, but I mean, first lecture I actually mentioned this, but now you can prove this, that if it is isolated, then you take 1 by f and then you extend that function to the whole polydisk, something like that. So you can try that. And all right, I stop here.
Thank you, Agniva. Any questions? Okay. So again, I have one question.
Yeah.
So yeah, so it's about the like from so yeah, weak domain of convergence, from weak domain of holomorphy to domain of holomorphy.
Right.
So yeah, so like you said that in the planar case, we have like every domain is a domain of holomorphy.
Yes.
So yeah, so basically that means that for every domain we can basically make the boundary as a natural boundary.
Yeah. Yes.
Yeah. So like, and in this theorem you basically like when you were discussing this one, you said that we cannot take the boundary points and just patch it to get the
exactly
desired function, but
exactly.
that we can so that is the difference between one and several, that actually in the one variable this we can do.
No, I mean, technically you can, but the patching up means you have to use something else. I mean, the way it patch up in the multivariable calculus or in manifold, in real manifold, what you do, you just take a cutoff function and apply a partition of unity. You cannot use the partition of unity over here. That's what my point. That to apply partition of unity, you need a cutoff function, and you don't have holomorphic cutoff function over here.
Okay.
Even in complex.
Okay, I was confused because I was thinking that in the planar case, the way we prove the domain of holomorphy for any domain, that way doesn't work.
No, that way doesn't work. I mean, there are again this in fact give you a particular domain. Constructing this function will be extremely hard. For a ball, for a disk, you can construct easily, but if I give a completely arbitrary domain, it's, I mean, I won't say for the disk even it's very easy. It's not very easy. I think probably summation z to the n factorial or something like that probably work. But
or z to the power is Hadamard theorem.
But for any abstract domain, it's not very easy.
But we can
again, you need
Metcalfe
these multiple different like equivalent conditions. Then things get easier. I mean, for one variable.
So planar domain we basically use Metcalfe, no?
Yeah, exactly. I mean, that's a big theorem to use Metcalfe to.
So any higher dimension version is not there.
No. It's probably. I mean, in higher dimension, I haven't seen any Metcalfe like that.
Yeah, I mean that I understand.
Yeah.
Okay, thank
you. Yep.
So I don't think we have any other questions. So thank you, Agniva, and we will meet in the next lecture.
Yeah, sure. Thanks.
Yeah, thank you.